Alright guys, I'm going to go over that problem at the very end of relative velocity in this video, and then I'm going to do a second problem where they're not nicely along the cardinal direction, so you can use the timestamps below to flip to specifically what it is that you need. Also, you can kind of use this video as well as a simple vector addition kind of video, and so if that's all you need, skip the relative velocity stuff and the timestamps and just go straight to when we're doing the vector addition. All right, so in this problem, what we have is a river flowing west, and the river is flowing at, let's say, 5 meters per second, okay? And the boat, or somebody in the water right here, is traveling at 3 meters per second. And the question on the table is, what does this person standing on the side of the river see the boat do? Now, most people can intrinsically know that it's going to go kind of at an upward right diagonal. It's probably going to head this particular way. But what we want to do is we want to, again, focus on this very, very mechanically. So if a problem is not necessarily intuitive, we can use it to figure out the answer and then work our way backwards and figure out why that was in fact the case. So the first thing that we do is we set up our equation. The purpose of setting up this particular equation is to figure out, do we have everything that we need, or do we need to maybe rotate a vector or something like that? So let's begin with figuring out what is the velocity that we want. Well, for starters, I asked how fast the boat is going, so we definitely need to see the velocity of the boat. The first subscript is the object in motion. Okay. The second one in this particular case is who would see that object in motion. And since we talked about this particular person right here, we could say person or you or Timmy or Kylie, but every single person, the person and everything around them is going just as fast as the Earth. So let's just go ahead and use the Earth as a frame of reference. Okay, let's start off with let's go to the next easiest, the river. Okay, what is this the velocity of? Well, I just said it, it's the velocity of the river, but the next question is, who would see the river going that fast and in that particular direction? For example, the person in the boat won't see it going that fast. And as a matter of fact, I don't think actually, well, that's confusing. We're not going to go in that. The velocity, this should be the velocity of the river seen by this person right here. So this is the velocity of the river either compared to person, or since we've already used Earth, the velocity of river compared to Earth. All right, now what about this yellow one right here? What about this? Who would see this? Well, for starters, we know this is the velocity of the boat. Shouldn't have any issue with that. But you might even say, well, that's the person sitting in the boat. Nope, it would not be the person sitting in the boat, because yes, that's how they are pushing. They are seeing themselves, they're trying to row straight across, aim right, say, at this tree, but we know they're not actually going to get there. They're going to land somewhere down the river over here. So who would see them? It would be someone that was actually swimming in the water or the river. So this would actually be the boat compared to river. Now, making that equation, as we talked about in class, we'll get very mechanical with it. We're trying to figure out what is the velocity of boat to Earth. So what are the mechanics of this? The first letter of what you're trying to find should be the first letter of your equation. The second letter of your equation should be your third frame of reference. So we have boat, we have Earth. The third frame of reference is the river right here. So we have boat compared to Earth is equal to boat compared to river. And then we will add the velocity of river compared to Earth. The first letter and the last letter of your equation should be the first letter and the last letter of what it is you're trying to find, while the middle letter right in here should be that third frame of reference. Past this point, this is just a vector addition problem, because if you note carefully, you will see that these are all vectors, meaning this 5 meters per second is actually west or to the right. So you could say west or to the right, or we could say at 0 degrees. I'm sorry, west, not west, east. It would be going east in this particular case. Man, I'm messing up my cardinal directions. And this 3 meters per second right over here would not be north, but at 90 degrees. So now I can take the vector BR, which is 3 meters per second at 90 degrees and add the vector 5 meters per second at 0 degrees. Now, if we just sketch this, what we should get, I'm going to start with this one right here, is, okay, here is the velocity of river compared to Earth. And from the end, vector addition, we would go up because that's 3 meters per second. Oops, labeling it differently. Velocity of boat compared to river. And the resultant is exactly what we said a second ago. We expect the boat to go up and right. So the boat goes up and right. So let's do the component vector addition real quick. Let's use a different color here. Let's use yellow. So we're going to use the velocity of river compared to Earth in the x, and that's easy. It's all in the x, so this should just be some basic trig here, positive 5 meters per second x hat. Velocity of river on the Earth compared to the y is equal to 0. It's not moving in the y at all. And velocity of boat compared to river in the x is also 0, since it's not moving in the x. And velocity of boat compared to river in the y, it's all in the y, so it should be positive 3 meters per second y hat. Now this seems a little bit silly when you already saw that this is a 90-degree triangle and you could just use basic trig, yada yada, and so forth. But as you'll see in the next example, it doesn't always work out this easy, so we should definitely know kind of what this technique is. The next step, after splitting all of your vectors into their relative components, is to add up all the x's and all the y's. Now again, this is very easy because one of them is going to be 0. But in this case, we have positive 5 meters per second x hat plus 0 meters per second x hat is 5 meters per second x hat in total. And y total is going to be 0 meters per second y hat plus 3 meters per second y hat is equal to a total of 3 meters per second y hat. And then, to get the magnitude, if we have the x and the y, the magnitude is going to equal the x total squared plus the y total squared, square root. So we get 5 meters per second x hat squared plus 3 meters per second y hat squared, square root, the whole thing. I don't have a calculator on me, so I'll simplify this later. That's 25, that's 9, so this would be the square root of 34. There, put meters on the outside. So it should be a little bit under 5. And I'll grab my calculator in a second because I am going to need it definitely for the next part. The angle is equal to the inverse tangent of, now this is where you might have asked the question, why on earth, when I made this equation, did I draw this second vector first? Okay, and the answer is because I wanted this along nicely along the x, so I could measure that angle right there. You don't have to do that. You technically could have made it like this. The problem is when you do that, if you do trig, x is actually the opposite for that angle. And usually we almost always make the y the opposite, meaning we always do kind of our trig as though the angle is over here on the alpha. Y is the opposite, x is the adjacent. So that's what I'm going to do. So inverse tangent of the y, 3 meters per second y hat, over the x, 5 meters per second x hat, and that should be under 40, probably about 30 and change, but let's figure out what these answers are. Square root of 34 is actually 5.83 meters. Inverse tangent of 3 over 5 is 30.96, we'll just say 31 degrees. Now, when you do this, because you can measure angles in different spots, here's what you want to write. Sorry, it's meters per second. 0.83 meters per second at 31 degrees from the river. Meaning, what I'm saying is, we are measuring this angle right here, this angle right here, or, going back to our original drawing, that angle right there, because it's being measured from the river. If you had done this other triangle, there is technically no problem with it. I have no issue with it whatsoever. But what you're going to find is that this angle here is the complementary of it. This is going to be 59 degrees. And 59 degrees is not wrong as long as instead of 31 degrees from the river, you say 59 degrees from the direction of the boat. So both 31 degrees and 59 degrees are correct as long as you give this extra context. And if you don't give that context, neither of them are technically correct. Let's do another problem. In this particular problem, let's imagine that you're Superman or some superhero that can fly directly up above. And we are looking down on the Earth. So we're going to use our cardinal directions right here. North, south, west, east is on the right, Spain. So you're looking down on the Earth like it's a map. And a villain has, in a semi-truck here, kidnapped a dog. The truck is traveling 30 miles an hour north. And this little dog is bored because he's been in there a while. Perfect dog, don't at me. And he's actually moving this way. I'm going to say he's moving. I'm going to draw it underneath over here. He's moving at 5 miles an hour at 30 degrees west of south. Now, the reason I say west of south and not directions that you're probably a little bit more used to is that in the context of this problem, this makes more sense. It makes more sense of saying like, hey, I'm going 30 degrees to the right or left or that type of thing. So what this really means, if you laid it out on a grid, is you start from south and you measure 30 degrees west. This is another way of saying negative 30 degrees from the negative y-axis. It tells us to start there. It tells us to go clockwise in this case, but obviously this way of writing it is sort of dumb. Erase, please. Relative to west of south makes a lot more sense in the context. Now, 30 degrees west of south is not necessarily going to help us on our trig, but we will come back to that when we get to it. All right, so let's go back and discuss how do we create that original equation. Firstly, what are we looking for? I don't think I told you that yet. You're a superhero up here in the sky. Okay, you're floating, and obviously you're above it. That's 3D perspective. Let's just, as you're looking at the picture, you sitting there watching the video are the person, you're the superhero looking at it. And the question is, how fast is the dog going to you? So what is the velocity of dog relative to the superhero? But again, you're not moving at anything compared to the Earth, so let's just say the dog compared to Earth. And let's label what else we have. What is this? 30 miles an hour north. This would be the velocity of the truck as seen by somebody on Earth. Or you, the superhero, would see the truck going that fast. Who would see the dog going this fast? Somebody who's also in the truck. So this would be the velocity of dog compared to truck. So we create our equation. Velocity of dog compared to Earth is equal to, first letter, dog. Third frame of reference, we've already done dog and Earth, so that'll be compared to truck, plus the velocity of truck compared to Earth. Let's check if we have these things that we need. Do we have dog compared to truck? Boom, it's right here. Do we have truck compared to Earth? Boom, it's right there. What does that mean you do now? Now we are simply at a vector addition. To make my vector addition a little bit simpler mechanically though, we don't want to keep this north around or this west of south. North will trade to 30 miles an hour at 90 degrees. And west of south will trade to 5 miles an hour at 240 degrees. That 240 degrees, because as I showed, we start at 270 and subtract off 30, and we're over here in that third quadrant. Now we simply need to do a vector addition. So we're going to come over here to the right and focus on that vector addition. This is the velocity of truck compared to Earth. This is the velocity of dog compared to truck. And the first thing we do is find the two separate components. Now you can either, like I kind of did on the last problem, go truck compared to Earth in the x, or if you want, make your life a little bit simpler here. And let's just call this is x1 and y1, and we'll just use this first vector right here. Now I can punch this in my calculator. I really don't need to. I know that that thing is going straight up. Okay, this is the velocity of truck compared to Earth. And so the x is simply going to be 0, and that's exactly what it's going to tell you when you punch it in. Okay? And the y is all in the y, and it's going positive. It should be positive 30 miles an hour y hat. Now, if you don't know how I kind of got there and you want to work through the mechanics, I'll show it to you over here on the right, but it will end the exact same way. What you would write is 30 miles an hour cosine of 90 degrees. And 30 miles an hour sine of 90 degrees. But if you followed our trig video the other day, you'll notice that this goes to 1. Sorry, this goes to 0. Cancels the whole thing out. And this goes to 1, leaving just 30 in that particular case. But these next ones I'm definitely going to need to use my calculator. x2, or this guy, will be 5 miles an hour cosine of 240 degrees, and 5 miles an hour sine of 240 degrees. I don't know why I started writing 90 there. So let's go ahead and punch those in to a calculator. I think this is actually, well, this is a 30, 60, 90. So what is that? 60, so the x is probably going to be half that. It's going to be negative 2.5 if I'm not mistaken. 5 cosine of 240. Yep, negative 2.5, or half of 5. And the y is, well, I can't do square root of 3 over 2 in my head, so 5 sine of 240, negative 4.33 miles per hour in the y hat. The next step of the vector addition, add all your x's and add your y's. So x total is simply going to be 0 miles an hour x hat minus 2.5 miles an hour x hat. And y total is going to equal 30 miles an hour y hat minus 4.33 miles an hour y hat. And x total should be negative 2.5. Fives are always messy when I write this. Miles an hour x hat. And the y is going to be 25.67 miles an hour y hat. Okay, so then I'll get my magnitude, r. R is going to be x total squared plus y total squared, square root. Square root the whole thing. And I get 25.8, which is, by the way, not that much different than that, which makes sense because that side is not very big. But that is still bigger, 25.8 miles an hour. And my angle will be the inverse tangent of y, which is 25.67 over x. So the inverse tangent, warning ahead of time, it's going to screw up, actually tells me negative 84.4, which is down in the fourth quadrant. Now you'll remember we talked about this the other day. Your calculator screws up the second and the third quadrants because of the signs on this. It just sees a negative and the negative puts it over here in the fourth quadrant. Now the solution is simply add 180, and that's going to put it over there. So let's take that 84, add 180, and you get 95.56. 95, let's just go 95.6 degrees. So our final answer is that the dog is traveling 25.8 miles an hour at 95.6 degrees. Why the heck? All right, so I focused on mechanics. Let's break down why this actually does in fact make sense and how you should know this is in fact the answer. You are a superhero watching a dog. The dog is traveling crazy fast up. What we did in the vector addition is we took this vector right here, pointed up, and we said we're going to add the dog compared to truck. So from right here, we said we're going to go down just a little bit. So why should the dog be considered going left? Because he's moving a little bit left. Why should he still mostly be going north? Because the dog is traveling nowhere as fast as the truck is going north. The truck is going 30 miles per hour north. Well, the dog's only moving 5 miles an hour, which is also pretty quick for a dog, so it must be running towards the back. Up. Now, why should we see the dog go slower? This is kind of like a person moving backwards on a treadmill. If the treadmill's going like crazy fast that way at 8 meters per second, and you're only running this way, say at, 6 meters per second, we should still see you going now slower, but still the same way. Just like we see the dog here, still going the same way, or at least up, but going slower. So there it is. This is just a vector addition. The velocity of truck compared to Earth plus the velocity of dog compared to truck yields the velocity of dog compared to Earth. And there you go.